Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stack series. Today we are exploring the science and design of interfaces, from atomic surfaces to human-computer interactions.
Thank you. It's great to be here to unpack this with you.
So imagine you have a solid brick of gold just, sitting on a table in front of you. If you want to melt that gold down, you have to heat it up to a very specific, totally unforgiving temperature.
Right, which is exactly 1,064 degrees Celsius.
Exactly. And it doesn't matter if you have a massive, 10-ton bank vault door made of gold or just a tiny 1-ounce coin. The classical laws of physics tell us that bulk gold melts at that exact temperature.
Yeah, that's what we're all taught.
But if you take a microscopic flick of that exact same gold, I'm talking about a nanoparticle so impossibly small it measures less than 50 nanometers across, the laws of physics seemingly just break.
They completely break down.
Right. Suddenly, that tiny piece of gold melts hundreds of degrees colder. It turns into a liquid, while the larger brick sitting right next to it remains completely solid.
It's a phenomenon that it really shatters our basic intuition about how the material world is supposed to behave. The rules that govern the bulk of an object just do not apply when you reach the extreme boundaries.
And that really is the core of our exploration today. We're going to look at what happens at the boundary where two different environments meet.
Which we call an interface.
Exactly. Whether we are talking about the chaotic surface of a metal nanoparticle, the microscopic edge of a liquid droplet, or, the glowing digital screens that visually impaired users rely on to navigate a busy street, the interface is where all the friction is. It's where all the action happens.
It really is the frontier.
Yeah.
And to truly grasp how these boundaries shape our reality, we really have to start at the physical foundations. We have to understand the underlying mechanics of what a surface actually is before we can even begin to map those principles onto digital architecture.
Okay, so let's ground this in something you, the listener, can probably see right now. If you're listening to this and you have, a cup of coffee or a glass of water sitting nearby, just take a look at the top of the liquid.
Right, the exact place where the water stops and the air begins.
Yeah. We totally take for granted that the liquid just sits there peacefully. But at the molecular level, there is this violent, continuous physical struggle happening right at that boundary layer.
To really conceptualize that struggle, we first need to look at the molecules deep inside the glass, down in what we call the bulk of the liquid.
Okay, so way down at the bottom of the cup.
Exactly. Down there, a single water molecule is entirely surrounded by other water molecules. It has neighbors above it, below it, to the left, to the right.
And water is polar, right? So it's actively bonding with all of them.
Yes, it forms hydrogen bonds with all those neighbors. And because it's surrounded on all sides, the molecular poles are totally symmetrical. The forces essentially cancel each other out.
Leaving the molecule in like a state of perfect balance.
Right, a state of thermodynamic balance.
So the net force on that bulk molecule is basically zero. It's perfectly suspended and structurally supported from every possible angle.
Exactly. But now, trace your way up to the very top layer of molecules, the ones directly touching the air. The physical reality for these surface molecules is, well, it's drastically different.
Because they're exposed.
Yes. They have neighbors below them and neighbors to their sides, but there's practically nothing above them, save for, a few sparse gas molecules in the air.
So they are missing half of their structural support system.
Precisely. And because they lack those upward connections, those surface molecules experience a massive net inward pull toward the bulk of the liquid. Plus, they feel a really strong sideways pull from the neighbors right next to them on the surface.
I always picture this like a giant circular game of tug-of-war. If everyone in the outer ring is pulling tightly inward toward the center, the whole ring is under this immense tension.
That's a great way to visualize it.
Or think of a stretched rubber sheet covering the top of a drum. The tension is constantly pulling inward and sideways, right? It's trying to make the surface as small and tight as physically possible.
And that cohesive elastic behavior is exactly what we define as surface tension. The liquid is actively trying to minimize its surface area.
Why does it want to minimize it so badly, though?
Because, fundamentally, maintaining a surface requires energy. The bulk state, being surrounded inside the liquid, is the lowest energy, most stable state. Being out on the surface is a high energy, totally unstable state.
Oh, I see.
This is actually why water naturally forms spherical droplets when it falls through the air. Geometrically speaking, A sphere is the shape that has the absolute minimum surface area for a given volume.
And understanding that surface tension, it isn't just about knowing why rain falls and drops, right?
Yeah.
This high-energy boundary dictates major physical phenomena that you, listening right now, rely on every single day.
Oh, absolutely. Capillary action is a perfect example of this.
Right. If you've ever wondered how a towering redwood tree can pull water from its roots like hundreds of feet up into the air, completely defying gravity, it all comes down to interfacial forces.
Exactly. The water molecules at the interface are actually more attracted to the solid cellulose walls of the plant's microscopic tubes than they are to each other.
So they literally pull themselves up the walls.
They do. And because of that high surface tension we just talked about, they drag the rest of the water column up right behind them.
It's incredible. And it scales from the tallest trees in the world all the way down to human biology. Think about the alveoli in your lungs.
Right, the microscopic balloon-like air sacs where oxygen actually enters your bloodstream.
Yeah. The inner lining of those tiny sacs is coated with a really thin film of water. And according to Laplace's law, the pressure inside a spherical bubble is directly proportional to its surface tension.
Which present a huge biological problem. If the surface tension of that fluid layer in your lungs was just left unchecked, that inward pull would be incredibly strong.
So strong that the tiny alveoli would just collapse under the pressure?
Exactly. Much like a deflated soap bubble.
Which means, practically speaking, you physically wouldn't have the muscle strength in your diaphragm to pull them open again. You wouldn't be able to breathe.
To prevent that collapse, human biology evolved to synthesize a complex mixture of lipids and proteins. We call it pulmonary surfactant.
And what does the surfactant actually do at the boundary?
The cells in your lungs actively secrete the surfactant directly into the water film. The molecules embed themselves into the water-air interface, physically interrupting the hydrogen bonds between those surface water molecules.
So it breaks up the tug of war.
Precisely. It drastically lowers the surface tension, allowing the alveoli to inflate with minimal effort. The mechanics of human breathing are, quite literally, entirely governed by the manipulation of a microscopic interface.
Wow. And this brings us to a crucial thermodynamic principle that really applies across all materials. Creating a surface requires work. You have to expend energy to break a material apart and expose new surface area.
Yes. And because the surface requires so much energy to exist, the molecules there are fundamentally more reactive. They are desperate to bond with something, anything really, to lower their energy state.
And that process is known as adsorption, right? With a D.
Adsorption, yes. Now, the reactivity of liquids is fascinating, but when we shift our focus to solid boundaries, the physics becomes even more extreme. In the scientific literature, the surface of a solid is often referred to as the chaos of the edge.
The chaos of the edge. I love that term. Let's visualize that. Imagine a solid block of metal, like aluminum or iron. Deep inside that block, the atoms are arranged in a perfect, repeating geometric grid.
Right, which we call a crystal lattice.
Yeah.
It is highly ordered and very predictable.
But when you reach the edge of the metal, that perfect periodic arrangement is just violently, abruptly interrupted.
The lattice just stops. It terminates. And the immediate consequence of this termination is the creation of what physicists call dangling bonds.
Dangling bonds.
Yeah. Inside the bulk, an atom shares its electrons perfectly symmetrically with all its surrounding neighbors. But at the surface, the atoms have valence electrons protruding out into empty space.
Because there's no neighboring layer of atoms there to complete the bond.
Exactly. They're essentially reaching out into the void, looking for a connection that just isn't there.
So what happens to those electrons? They can't just hover there doing nothing, can they?
Well, these dangling bonds create localized electronic properties known as surface states. And the electrons trapped in these surface states operate under entirely different quantum mechanical rules than the electrons moving freely deep inside the metal.
Okay, so to understand and predict how these boundary electrons behave, I know solid-state physicists rely heavily on this foundational theoretical framework. It's called the Jellium model.
The Jellium model, yes. It's essential for this kind of work.
Let's unpack the Jellium model for a second because, honestly, it sounds like a sci-fi concept, but it's actually this brilliant mathematical simplification.
It really is. Because in a real piece of metal, you have billions of positively charged atomic nuclei, the heavy centers of the atoms arranged in a grid.
Right, and swarming all around them is this fluid-like sea of negatively charged electrons.
And trying to calculate the interaction of every single electron bouncing off every single discrete positive nucleus,
Yeah.
It's computationally impossible.
It would just melt any supercomputer on Earth.
Exactly. So the Jellium model removes the individual discrete positive nuclei entirely. It just smears them out.
It smears them out.
Yeah, mathematically speaking. It assumes that the positive charge of the metal is just a uniform, continuous, perfectly flat background, basically like a continuous block of positively charged jelly.
Ah, hence the name Jellium. So you smooth out all the microscopic atomic speed bumps into this perfectly flat road, and then you just observe how the traffic, the negatively charged electrons, behaves on that road.
That's a great analogy.
Mm.
And observing the electrons at the boundary of that flat road reveals some incredible insights.
Like what?
Well, in the Jellium model, the positive jelly stops at a hard mathematical edge representing the surface. But the electrons don't respect that hard boundary.
Because they're quantum, right?
Right. Because electrons behave as quantum mechanical wave functions, they cannot simply drop to zero instantaneously. Their charge density actually spills out past the positive edge, extending a tiny distance into the vacuum of empty space before finally tapering off.
It's kind of like filling a swimming pool right to the absolute brim, and a little bit of the water naturally sloshes over the edge onto the concrete.
Yes, and that spilling creates a massive electrical consequence. You now have a microscopic layer of negative charge sitting just outside the metal and a corresponding deficit of negative charge, meaning a relative positive charge sitting just inside the boundary.
So it separates the charges right at the edge.
Exactly. This creates a highly localized electric dipole layer right at the surface.
And this isn't just some abstract theory, right? This dipole layer dictates a real physical, measurable property called the work function.
Yes, the work function is critical.
Mm.
If you want to build a solar panel or really understand the photoelectric effect, you absolutely have to know the work function.
Which is, simply put, the absolute minimum amount of thermodynamic work, or energy, required to physically rip an electron through that dipole layer and out into the vacuum at absolute zero temperature.
Exactly. Now, the Jellium model also exposes another wild phenomenon called Friedel oscillations.
Friedel oscillations. Break that down for us.
So when you look at the electron density right near the surface, it doesn't just smoothly decrease as it hits the boundary. As the electron waves crash against the inner wall of the surface, they actually reflect back and interfere with themselves.
Like dropping a stone in a pond and watching the ripples hit the edge and bounce back.
Exactly like that. It creates a rippling, standing wave pattern of electron density just inside the metal. These are damped oscillatory structures.
Meaning they fade out the deeper you go.
Yes. The density of the electrons peaks and dips repeatedly as you move away from the surface inward. And the intensity of these ripples depends heavily on the density of the metal itself, which physicists often quantify using the Wigner-Seitz radius, denoted as Sevizellers.
Okay, hold on. Let me stop you there just to clarify for the listener. What exactly is the Wigner-Seitz radius, or Sevizellers in like plain English?
Sure. Think of it as a measure of personal space for an electron. It is the radius of a theoretical sphere that contains exactly one electron.
Okay, so it's about crowding.
Right. If Furs is a small number, like 2, it means the electrons are packed very tightly together. This is a high-density metal, like aluminum.
And if it's larger?
If Furs is a larger number, like 5, the electrons have a lot more breathing room. This is low-density metal, like cesium.
So the computational value essentially just tells us how crowded the electron sea is.
Precisely. And the computational models show that the Friedel oscillations, those quantum ripples crashing against the surface, are significantly stronger and much more pronounced in low-density metals, where the trivial value is around 5.
Because they have more space to move.
Exactly. The electrons have more room to slosh around, so the resulting waves are much larger than in a tightly packed, high-density metal.
That makes total sense. But even with the Jellium model smoothing things out, I know material scientists eventually have to model real, discrete atoms to build actual workable technologies. How do you simulate a real solid surface on a computer without the machine just completely crashing?
That's where they utilize the slab and supercell approach. Instead of trying to simulate an entire macroscopic block of metal, researchers create a mathematical model of a very thin, perfectly flat slab of atoms.
So they just mathematically slice a microscopic layer off the top.
Right. But there are very strict geometric rules. The slab must be mathematically thick enough, usually several atomic layers deep, so that the atoms in the very center behave as if they are deep inside a bulk material.
You have to be completely unaware of the surfaces above and below them.
Exactly. If the slab is too thin, the top surface and the bottom surface will electronically interfere with each other, which completely corrupts the data.
So you need a thick enough slab to act as a buffer, And then how do you simulate the vacuum above it?
Well, the computer calculates an infinite repeating array of these slabs using periodic boundary conditions. It basically stacks them like a skyscraper.
Okay.
But to simulate the surface, it inserts a massive gap of empty mathematical space, a vacuum layer, between each and every slab.
So they aren't touching.
Right. And this vacuum gap must be wide enough so that the electron density spilling out from the top of one slab doesn't accidentally interact with the bottom of the slab hovering above it.
Wow.
It really is a delicate computational balancing act to optimize the thickness of the material against the thickness of the void.
Okay, so this gives us a really solid, rigorous understanding of physical interfaces. We know that boundaries dictate behavior. They are these high-energy zones filled with dangling bonds, rippling electron densities, and immense tension.
They absolutely govern what enters and what exits a system.
Exactly. Now, I want to bridge this physical reality directly into the digital world, because the exact same conceptual architecture applies here.
It really does.
A physical surface mediates the physical world. It dictates how a water drop interacts with a leaf, or how light interacts with a metal. In the exact same way, a user interface, or UI, is the boundary that mediates the digital world. It is the surface through which human intent translates into machine action.
That is a highly functional parallel. In digital architecture, the surface is the curated arrangement of pixels, interactive elements, and navigational architecture.
Right.
And just as physicists work to calculate the stability and thermodynamic limits of a metal slab, digital designers work to engineer what we term a sustainable user experience, or sustainable UX.
And a huge part of achieving that stability today relies on responsive web design, or RWD.
Responsive web design is basically the methodology of building a singular digital interface that dynamically reshapes and reorganizes itself.
To sustain a high-quality experience across multiple terminals, right?
Exactly. Whether you are looking at a website on a massive 32-inch curved desktop monitor, a tablet, or a tiny smartphone screen while riding the subway, the interface has to physically adapt to the constraints of the hardware.
To really understand the anatomy of this digital surface, I was looking at this comprehensive study where researchers categorized 40 different responsive interfaces. They wanted to isolate the foundational layout factors.
They're essentially identifying the digital atoms that make up the screen boundary.
Exactly. And the empirical data from that analysis provides a really clear taxonomy of digital interfaces.
Yes. Across the 40 responsive sites analyzed, specific structural elements were basically non-negotiable. For instance, navigation bars and banners were present in 100% of the analyzed interfaces.
Which makes perfect sense. Without navigation, you don't really have an interface, you just have a digital painting. The navigation bar is the physics of movement in the digital space. It's what allows the user to traverse the architecture.
Similarly, content blocks and interface layout elements were also present in 100% of the sites. These are the load-bearing pillars of the design.
Right.
Moving down the hierarchy of necessity, logos appeared in 80% of the sites, search tools in 60%, and footers in 50%.
But the metric that really stands out from this study, the one that bridges our physical and digital worlds perfectly, is interface density.
Yes, interface density.
It was identified as a primary governing factor in 70% of the designs. I want you, the listener, to visualize your smartphone right now. Think about your favorite app. When you open it, there is a very specific volume of information, text, icons, video, thumbnails, buttons packed into that limited physical space.
And that, simply put, is interface density.
Right.
And that density has an immediate, measurable impact on the human interacting with it. In physical chemistry, the atomic density of a metal surface, the Wigner-Seitz radius we discussed earlier, dictates its thermodynamic energy, its work function, and its Friedel oscillations. Well, in digital design, interface density dictates the cognitive load demanded from the user.
If the screen is packed with too many overlapping menus, auto-playing videos, and tiny buttons, the interface density is just too high. The user's cognitive load spikes. It takes way too much mental energy to find the one piece of information they actually want.
And conversely, if the density is too low, the user has to scroll endlessly through empty white space to achieve their goal, which also leads to severe frustration.
So the boundary is unstable in both extremes.
Exactly. Managing that density across varying screen sizes is the defining challenge of sustainable UX.
Okay, this sets our stage perfectly. We understand the foundations now. Interfaces are high-energy boundaries that govern the stability of a system, whether that system is a droplet of water, a metallic crystal, or a smartphone screen.
Right.
But, science and design are not static fields. They are constantly evolving, which brings us to the second phase of our journey, the active debate. We are moving into the territory where the leading scientific minds vehemently disagree on the fundamental mechanisms of reality.
And in physical chemistry, the most intense ongoing debate currently centers around the exact physical mechanisms of phase transitions at the nanoscale.
Specifically, the mystery we touched upon at the very beginning of our discussion, melting point depression.
Right, the gold nanoparticle. We established that bulk gold melts at 1064 degrees Celsius, but a nanoparticle under 50 nanometers melts at a drastically lower temperature.
Why does size change the fundamental melting point of an element so drastically?
The why is rooted in the thermodynamics of the surface atoms we explored earlier. Remember the dangling bonds?
Yeah, reaching out into the void.
Exactly. The atoms on the surface of the nanoparticle have far fewer nearest neighbors than the atoms locked safely inside the core. Because they have fewer neighbors sharing electrons, they have significantly lower cohesive energy.
They are not held as tightly to the structure.
Right.
Going back to our analogy, they are the outer ring in the tug of war, and they basically only have half a team holding them back.
To quantify this mathematically, physicists utilize what's called the Lennard-Jones potential. This is a model that calculates the intermolecular potential energy between two atoms based on their distance from one another.
Okay, so it looks at the space between them.
It accounts for both the attractive forces that pull the atoms together and the repulsive forces that push them apart when their electron clouds get too close. The Lennard-Jones potential essentially maps out the energetic depth of the bonds holding the solid lattice together.
Okay, so the Lennard-Jones potential tells us how deeply entrenched and stable the atoms are. But how do we get from there to actual melting? What's the trigger?
To find the trigger, we apply Lindemann's criterion. Frederick Lindemann proposed a theoretical threshold for melting over a century ago.
And what does it say?
According to Lindemann's criterion, a solid crystal begins to melt when the thermal energy introduced into the system, the heat, causes the atoms to vibrate so violently that the root mean square amplitude of their vibration exceeds a critical fraction, which is usually around 10% of the distance between the neighboring atoms.
Oh, I see. When you heat up the gold, the atoms start violently shaking in place. And Lindemann's criterion basically says that once they shake so hard that they are swinging more than 10% out of their normal position, the bonds just snap.
The lattice collapses.
Yeah.
The solid becomes a fluid.
Got it.
And because the surface atoms already have significantly lower cohesive energy due to those missing neighbors we talked about, their Lennard-Jones potential wells are much shallower.
Which means?
Therefore, it requires far less thermal energy, far less heat to make them vibrate past Lindemann's 10% threshold. They break free much sooner than the bulk atoms.
And because a tiny nanoparticle is essentially all surface area,
Yeah.
a massive percentage of its total atoms are sitting on the edge compared to a giant brick of gold, the entire particle requires much less total energy to melt.
That is the fundamental consensus. Science widely agrees on that.
But the active debate is about the how, right? What is the exact sequence of events when, say, a 20 nanometer particle melts? Which atoms move first, and where does the liquid go?
Exactly. The scientific literature currently wrestles with 4 major competing theoretical models trying to explain this exact atomic mechanism.
Let's walk through these models, starting with the most macroscopic one.
Yeah.
The liquid drop model, or LDM.
The liquid drop model takes a very macroscopic thermodynamic approach. It posits that the entire nanoparticle transitions from a solid state to a liquid state entirely simultaneously at a single, specific depressed temperature.
So it doesn't melt layer by layer, the whole thing just instantly turns to a liquid drop?
Yes. The LDM argues that for very small particles, the overwhelming dominance of the surface energy dictates the stability of the entire system.
Okay.
When the surface reaches its critical instability point, the cohesive integrity of the entire particle fails at once. It treats the nanoparticle less like a complex crystal and more like a uniform, continuous droplet of matter.
It is the all-or-nothing model. But I know the second model completely disagrees with that simultaneous collapse. Let's look at the liquid shell nucleation model, or LSN.
The LSN model introduces distinct spatial and temporal dynamics. It argues that melting is absolutely not instantaneous across the particle.
What happens instead?
Instead, it asserts that the surface atoms melt first, because of their lower cohesive energy, forming a distinct, continuous shell of liquid metal surrounding a core that remains entirely solid.
So it looks like a microscopic piece of candy with a solid center and a melted exterior.
Exactly like that. And the LSN model utilizes Landau potentials, which are mathematical functions describing the free energy of a system as it undergoes a phase transition, to argue that this liquid shell is actually stable.
Stable how?
The model suggests that the boundary interface between the liquid outer shell and the solid inner core does not immediately move inward. The thickness of the melted shell is dictated purely by the particle's radius of curvature. The inner core will remain solid until additional higher thermal energy is applied.
So the LDM says it all melts at once. The LSN says the outside melts, forms a shell, and waits. But then we have the third model, which seems to combine and then violently reject parts of both.
You're talking about the liquid nucleation and growth model, the LNG.
Yes, the LNG.
The LNG model agrees with the LSN on one key point. Melting initiates at the surface. However, it vehemently disagrees that the resulting liquid shell is stable. The LNG model relies heavily on Gibbs-Duhem thermodynamic relations.
Let's pause for a second to make sure we don't lose the thread here. What exactly do the Gibbs-Duhem relations tell us?
In physical chemistry, the Gibbs-Duhem equation describes the relationship between changes in chemical potential, temperature, and pressure within a thermodynamic system.
How does that apply to the nanoparticle?
In the context of a melting nanoparticle, it allows researchers to calculate the immense pressure differentials and energy gradients that occur right at the microscopic boundary between the newly formed liquid and the remaining solid core.
Okay, so it essentially maps the invisible forces pushing against the solid center.
And according to the LNG model's application of those exact forces, the interface between the liquid shell and the solid core is radically unstable.
So it doesn't wait around like the candy shell.
Not at all. The model predicts that the moment liquid nucleation occurs on the surface, the interface does not wait, it cascades. The liquid boundary advances incredibly quickly, crashing inward through the rest of the particle like a wave, consuming the solid core in an almost instantaneous sweep.
That is highly dramatic visualization. It starts on the outside, but it infects the inside so fast it's practically a chain reaction.
Exactly.
And yet, there is a fourth model that approaches this entire problem from a completely different direction. The bond order length strength model, or BOLS.
The BLS model is fascinating. The first three models rely heavily on continuous thermodynamic equations. But the BLS model is an atomistic approach. It zooms in past the macro-level thermodynamics and looks exclusively at the individual discrete bonds between atoms.
It looks at the microscopic architecture.
Yes, and the BLS model proposes a highly counterintuitive mechanism. It argues that when an atom on the surface loses a bond, because again, there is no neighbor above it, it doesn't just weakly hold on to its remaining neighbors.
What does it do?
Instead, the atom compensates. The remaining bonds actually become shorter, and individually, they become stronger.
Wait, that makes no sense initially. If you knock out a supporting pillar in a building, the remaining pillars don't magically get stronger, they usually buckle under the stress. Why on earth do atomic bonds get stronger?
It is a quantum mechanical redistribution of electron density. Because the surface atom has fewer neighbors to share its electrons with, it shares more of its electron cloud with the neighbors it does have.
Oh.
This pulls them closer together, shortening the bond length and increasing the bond strength.
Okay, but if the individual remaining bonds are shorter and stronger, wouldn't that mean the surface is harder to melt? That contradicts everything we've established about melting point depression.
And here is the brilliant nuance of the BLS model. Even though the individual remaining bonds are shorter and stronger, the sum total of the cohesive energy for that atom still drops.
Because it simply has fewer bonds overall.
Exactly. Two very strong bonds still don't equal the combined cohesive energy of four regular bonds. The BOLS model meticulously calculates how these altered, tightened bond lengths propagate from the surface inward, creating a gradient of physical properties. It argues that melting point depression is not just a surface phenomenon, but the result of the entire internal lattice reorganizing its bond strengths to compensate for the chaos of the edge.
That's incredible. 4 incredibly complex models, all competing to explain the exact same drop in temperature. And what makes this active debate so relentless is that the rules change depending on what the nanoparticle is actually made of.
Absolutely. The models we just explored are primarily debated in the context of metallic nanoparticles, like gold or silver. But when material scientists study semiconductor or covalent nanoparticles, such as silicon or germanium, the physical behavior completely diverges.
How so?
For metals, empirical data shows that the melting point depression has a roughly linear dependence on the inverse of the particle size.
Meaning, as the particle gets smaller at a constant rate, the melting temperature drops at a constant rate.
Yes. But for covalent nanoparticles, the depression follows a quadratic dependence. It is a curved, accelerating relationship.
Why the difference?
This is because covalent bonds in silicon are highly directional and rigid, unlike the fluid, non-directional metallic bonds we saw in the gellium model. The directional nature of covalent bonds fundamentally alters how surface energy scales as the particle shrinks.
And beyond the material itself, the physical shape of the nanoparticle throws another wrench into all these models, doesn't it?
Oh, absolutely.
Yeah.
A perfect spherical nanoparticle melts very differently than a long cylindrical nanowire or a flat two-dimensional platelet.
Because of the surface-to-volume ratio.
Precisely. A sphere has the absolute highest surface-to-volume ratio possible, so the surface atoms completely dominate the physics, leading to massive melting point depression. But if you have a long nanowire, proportionally more atoms are safely tucked away inside the bulk of the cylinder, which actually suppresses the depression effect.
Furthermore, we have to talk about the substrate problem, because theoretical physicists love to run their models assuming a nanoparticle is floating completely isolated in a perfect empty vacuum.
Because it makes the math infinitely easier.
Exactly. But in reality, in any applied laboratory or manufacturing setting, nanoparticles are almost always resting on a physical surface, a substrate like a layer of carbon or silicon dioxide.
Right, and the energetic atomic interaction between the bottom of the nanoparticle and the top of the substrate inevitably alters the thermodynamics of the entire system.
Because they're touching.
Yes. Some of the nanoparticle's surface atoms are chemically bonding with the substrate, which changes their local cohesive energy, their Lennard-Jones potential, and consequently the melting point of the entire particle. The boundary condition is essentially contaminated by reality.
Contaminated by reality. I love that. It is an incredibly messy, evolving frontier. And I want to use that exact concept of constrained boundary conditions to mirror the active debate currently happening in digital UI design.
It's a very apt comparison.
We just explored how physical constraints, the size, the shape, the substrate, radically alter the structural stability of a nanomaterial. In the digital world, hardware and screen constraints radically alter the stability of the user's focus and the system's performance.
The parallel is very direct. The central debate in digital design currently revolves around aesthetics versus usability. This is the main battleground of sustainable UX.
Right.
As developers are pushed to create universally responsive interfaces that must function on everything from a massive ultra-wide curved monitor down to a tiny 1-inch smartwatch screen, they are constantly fighting a war of constraint management.
We talked earlier about interface density. The debate centers on how much functionality, how many features, layers of menus, and active visual elements you can compress into a highly constrained space before the system effectively breaks down.
You are constantly balancing high functionality against system latency and human cognitive overload. When an interface becomes excessively dense on a small device, two things happen.
What's the
First, the hardware struggles. Rendering a massive DOM document object model with overlapping CSS animations and heavy JavaScript execution requires significant processing power and RAM.
Right.
The mobile processor has to work much harder, which generates heat, throttles performance, and drains the battery rapidly. That introduces latency. The interface becomes sluggish and unresponsive.
And second, the human brain struggles. If a user is looking at a smartwatch and trying to decipher an interface packed with 6 microscopic icons, their visual processing is totally overwhelmed. It takes too long to execute a simple decision.
Exactly. We can view this through the lens of our earlier physics models. Just as a 10-nanometer gold particle experiences melting point depression and loses its cohesive structural integrity at a much lower temperature due to its extreme physical constraints.
A digital interface subject to extreme screen constraints experiences a functional breakdown much faster.
Precisely. The latency spikes, the cognitive load exceeds the user's threshold, and the structural integrity of the human-computer interaction simply melts away. The user abandons the task. The system fails.
It is the exact same fundamental problem. managing the energy, density, and stability of a boundary under severe physical constraints.
It really is.
Which brings us naturally to the third phase of our discussion, the frontiers. If we understand how physical and digital interfaces work, and we know exactly where the structural limits are, how are scientists and engineers actively manipulating these boundaries to create revolutionary new tools?
Let's start on the physical side with what researchers call smart physical interface.
Okay, let's dive into that.
One of the most dynamic and heavily researched frontiers in material science today involves the engineering of stimuli-responsive hydrogels.
To lay the groundwork for you listening, a basic hydrogel is essentially a three-dimensional network of cross-linked polymer chains that are incredibly hydrophilic, meaning they really, really love water.
They do. They can absorb and hold a massive amount of water without dissolving, much like a household sponge or a soft contact lens or even the gelatin you eat.
That is the foundation. But smart hydrogels are engineered at the molecular level so that the polymer network itself reacts dynamically and autonomously to specific external stimuli in its environment.
Yes. The interface of the hydrogel actively reads and responds to the world around it. The two most prominent triggers being utilized in medical research right now are temperature and pH levels.
So the hydrogel physically changes its shape, density, or porosity based on how hot or acidic its immediate surroundings are?
Exactly.
Wow.
They undergo a macroscopic phase transition driven by microscopic chemical changes. For example, consider a thermoresponsive hydrogel.
Okay.
It might be designed to be highly swollen and porous at room temperature, happily holding a massive volume of liquid. But if you raise its temperature slightly, say to normal human body temperature, the thermodynamics of the polymer chains shift.
What happens to them?
They suddenly prefer to bond with each other rather than the water. The network violently collapses inward, squeezing all the water out like a wrung sponge.
And that phase transition is incredibly useful for something like targeted drug delivery, right?
It is revolutionary for drug delivery. Consider a pH-responsive hydrogel engineered specifically to combat cancer. The microenvironment immediately surrounding a malignant tumor often exhibits a lower, more acidic pH than healthy blood or regular tissue.
That's a phenomenon related to the Warburg effect, right? Tumors produce excess lactic acid.
Exactly, the Warburg effect. Researchers can encapsulate highly toxic chemotherapy drugs inside the matrix of a smart hydrogel. This hydrogel is precisely engineered to remain tightly cross-linked and impenetrable at the neutral pH of normal human blood.
So it's sealed shut.
Yes. The drug travels safely through the circulatory system, securely locked inside the gel, completely inert, causing absolutely no systemic side effects to the patient.
But the moment that hydrogel drifts into the highly acidic microenvironment of the tumor,
The interface of the hydrogel reacts to the acidic boundary condition. The lower pH triggers the polymer chains to protonate, causing them to physically repel one another.
and it opens up.
The hydrogel rapidly swells and dissolves, releasing the chemotherapy payload exactly at the site of the tumor and nowhere else. The physical boundary of the material makes an autonomous, localized decision based purely on interfacial chemistry.
That is just,
Yeah.
it's precision medicine at the atomic level. It's amazing. Now, another major physical frontier mentioned in the literature involves emexene surfaces.
Emzenes, yes.
I want to spend some time here because this is relatively new. What exactly is an emzene? I mean, how do we even conceptualize that?
Emexenes, pronounced magzenes, are an incredibly exciting class of two-dimensional inorganic compounds. Structurally, they are just a few atomic layers thick, similar to graphene, but they are typically composed of transition metal carbides, nitrides, or carbonitrides.
How do you even make something like that?
They are synthesized by taking a bulk crystal, called a max phase, and using highly corrosive acids to literally etch out specific atomic layers, leaving behind an accordion-like stack of microscopic 2D sheets.
And why go through all the trouble of etching them? What makes these 2D sheets so special?
They possess a rare and highly sought-after combination of properties. They have the exceptional electrical conductivity of transition metals, but because they are heavily functionalized with oxygen and hydroxyl groups on their surfaces, they are highly hydrophilic.
Wait, so they mix with water?
Yes, you can actually dissolve these highly conductive metal sheets into water to create functional inks. They have massive potential for flexible electronics, next-generation supercapacitors, and advanced battery electrodes.
But they have a fatal flaw, right? A constraint holding them back.
Unfortunately, yes. Because they're only a few atoms thick, emphene sheets are inherently brittle. They cannot withstand significant mechanical stress.
And their surfaces are reactive.
Very reactive. When exposed to oxygen or water over time, they rapidly oxidize. They basically rust, degrading into useless titanium dioxide.
So how are materials scientists solving that? How do you protect a material that is literally only a few atoms thick?
By engineering a heterostructure interface, researchers are actively integrating these delicate 2D enzene sheets into highly engineered polymer matrices. They essentially soak the emexenes in specialized liquid polymers.
Okay.
The polymer chains intercalate, meaning they slide perfectly between the individual accordion layers of the enzene.
So you are basically wrapping the fragile 2D metal in a protective plastic casing.
It is much more dynamic than just a static casing. The polymer provides multidimensional stabilization. At the molecular level, the polymer chains actually bond with the surface functional groups of the enzene.
What does that do when it bends?
When the material is bent, twisted, or subjected to mechanical stress, the polymer chains dissipate that energy through reversible bond stretching. The viscoelasticity of the polymer phases absorbs the kinetic energy and mitigates stress concentration.
So it stops it from breaking.
Exactly, preventing the brittle enzene layers from fracturing or delaminating,
Oh.
which means peeling apart.
It's like building atomic shock absorbers right into the battery.
Exactly. And chemically, the encapsulating polymer matrix acts as an impenetrable physical barrier, sealing the emexene surface away from atmospheric oxygen and water, entirely suppressing oxidation and hydrolysis. The interface between the inorganic enzene and the organic polymer fundamentally solves the structural limitations of the material.
That's brilliant. I want to look at one more physical frontier before we switch back to the digital side. Let's talk about catalysis and the D-band model.
A classic interfacial problem.
Right. We established early on with our Gellium model that physical surfaces are high-energy zones filled with dangling bonds. Because those surface atoms are so desperate to bond, surfaces are the ultimate catalyst. They grab onto molecules flowing by, weaken their chemical bonds, and force them to react faster.
That is the very essence of heterogeneous catalysis. But the process is a delicate thermodynamic balancing act, governed by the Sabatier principle.
Explain the Sabatier principle for us.
A catalytic surface must be reactive enough to strongly grab onto the reactant molecules, a process called adsorption. But crucially, it cannot be too reactive.
Because then it gets stuck.
Yes. If the surface holds onto the molecules too tightly, the reaction happens, but the resulting product molecules can't break free. They just sit there, permanently poisoning and blocking the catalyst from doing any further work.
It has to be sticky enough to catch the fly, but weak enough to let it go once it's changed? How do scientists tune that stickiness?
For transition metals, which are the most common industrial catalysts, researchers utilize the D-band model, pioneered by Jens Nerskov and his colleagues.
And what is the D-band?
The D-band refers to a specific, narrow range of energy levels where the d orbital electrons of the transition metal reside. The theoretical model proves that the exact energy position of the center of this D-band, relative to the Fermi level of the metal, completely dictates how strongly or weakly molecules will bind to the surface.
So by manipulating the metal at the atomic level, scientists can actually shift the D-band up or down, dialing in the exact required stickiness for a specific chemical reaction.
Precisely. And we see the dramatic effects of this tuning when we look at specific atomic scale energetics. The research highlights iron-carbon, or FeC, nanoclusters, and iron-molybdenum nanotubes.
How does size factor into this?
If we connect this back to our earlier discussion on nanoparticles and size effects, it turns out that the physical size of the iron catalyst particle directly and strictly alters the D-band electronics.
As that changes the chemistry.
Yes, which in turn alters the thermodynamic solubility of carbon inside the iron.
So the size of the tiny iron bead literally determines how much carbon it can absorb. Why is that specific interaction so important?
Because that size-induced limitation represents the absolute thermodynamic bottleneck for manufacturing single-walled carbon nanotubes.
Oh, wow.
Carbon nanotubes are grown by feeding carbon gas over these microscopic iron catalyst beads. The carbon dissolves into the iron and then precipitates out the back to form a continuous tube. But if the iron catalyst particle is too small, the D-band shifts. The carbon won't dissolve properly, and the nanotube simply cannot grow. The atomic scale geometry and the quantum electronics at the interface dictate the absolute limits of our advanced manufacturing capabilities.
It all fundamentally comes back to the atomic surface. Okay, let's pivot from the cutting edge of physical interfaces to the absolute cutting edge of digital interfaces. We are moving beyond the screen
The natural user interface.
Exactly. We are moving away from the GUI, the graphical user interface that we have all used for decades with mice and touchscreens, and we are entering the era of the NUI.
An NUI is fundamentally designed to be invisible. Instead of forcing the user to learn the machine's language clicking arbitrary graphic icons with a mouse or a finger, the NUI allows the user to interact with the computational system through natural human behaviors.
Things like voice commands, spatial gestures, haptic touch, and environmental awareness. And while NUIs are becoming somewhat common with smart speakers in our homes, this frontier is producing absolutely life-changing, structural breakthroughs for visually impaired users navigating the real world.
It really is a paradigm shift for accessibility.
To understand this, we are going to look at the insights from a massive PRISMA systematic review.
PRISMA stands for Preferred Reporting Items for Systematic Reviews and Meta-Analyses. It is a highly rigorous, standardized methodology for synthesizing scientific literature.
And the scale of this review is huge, right?
The researchers conducting this specific review started with an absolute ocean of data. 3,125 published articles focused on assistive digital technology.
Wow.
Through incredibly strict inclusion and exclusion criteria, they filtered that massive pile down to just 106 peer-reviewed articles that genuinely push the frontier of multisensory NUI innovations.
The review makes one thing abundantly clear. The future of digital accessibility relies on entirely bypassing the visual cortex and the flat glass screen and instead synthesizing audio, haptic, and spatial feedback into a cohesive interface.
Yes, a fully integrated experience.
Let's break down some of the specific, fascinating applications highlighted in the research. First up, Guidecopter.
Guidecopter is a brilliant paradigm shift in navigation. It is a tethered, drone-based haptic guidance interface.
How does it work?
Traditionally, visually impaired individuals rely on a seeing eye dog or a white cane to detect immediate physical obstacles. The Guidecopter replaces those tools with a small, autonomous drone. The user holds a physical tether attached to the drone.
Okay, so they're physically connected.
Right. The drone uses advanced spatial orientation, LiDAR, and computer vision obstacle detection to perfectly map the environment, and it physically leads the user by pulling on the tether.
It provides haptic or touch-based directional feedback. You literally feel the drone guiding your hand around a pothole or a construction barrier. It moves the digital interface directly into the physical tension of a rope.
Exactly. Another remarkable application detailed in the review is Hear Me. This system tackles a critical, often dangerous everyday problem: medication management.
Because distinguishing between different prescription bottles is incredibly difficult for visually impaired users.
It is incredibly difficult and fraught with risk. Hear Me solves this using NFC near-field communication.
These are those tiny, cheap, powerless chips that can be embedded into stickers, right?
Yes. The NFC tags are attached directly to the medication packages. The user simply waves their smartphone over the tag.
And then what?
The phone's NFC reader powers the chip, retrieves the data, and the Hear Me system instantly provides clear, localized audio output. It reads out the name of the medicine, the exact dosage, the expiration date, and any essential warnings.
That's amazing.
It transforms a silent, inaccessible plastic pill bottle into an active speaking interface.
Next is an application called AirTouch, which I found fascinating because it solves a really nuanced problem that sighted people rarely think about: privacy in public spaces.
Privacy is a massive concern in accessibility tech.
Right. If you are visually impaired and relying on a standard screen reader on a crowded bus, the software is reading all of your private text messages, emails, and passwords out loud for everyone to hear.
The standard solution is wearing headphones. But headphones block out ambient environmental noise.
Which visually impaired users desperately rely on for spatial awareness and safety.
Exactly. AirTouch approaches the interface entirely differently. It allows the user to hold the smartphone up to their ear like a traditional phone call and privately control the device using touch gestures made directly with the ear against the screen.
Which requires serious software engineering because capacitive touchscreens are explicitly designed to reject large touch inputs, like a cheek or an ear, to prevent accidental dialing.
Exactly. The developers had to bypass and rewrite the capacitive rejection algorithms. The AirTouch system utilizes machine learning to recognize the specific spatial geometry and movement gestures of the ear itself.
So the ear becomes the finger, essentially.
Yes. The user can scroll or select items with ear movements, and the system triggers localized, low-volume audio output directly through the phone's earpiece speaker. It maintains absolute privacy without requiring headphones and completely eliminates the need for the user to look at or tap the screen with their fingers.
And finally, the Prisma review heavily highlights applications like Transmigria and various route planning apps.
Yes, for transit.
These tools utilize crowdsourced GPS geolocation and real-time transit data to help users navigate complex public transit systems, locate exact bus doors, and safely cross streets.
They're incredibly useful tools.
But I have to challenge the practicality here based on the constraints we talked about earlier.
Okay, what's your concern?
Well, a lot of these advanced NUI navigation systems rely on real-time computer vision. The phone's camera looks at the intersection, and AI processes the video feed, recognizes a crosswalk, and tells the user it's safe to walk. If that AI processing requires heavy CPU computation, or worse, if it relies on pinging a remote cloud server via a 5G network to process those thousands of images, doesn't that introduce a fatal flaw?
How so?
If someone is trying to cross a busy, chaotic intersection, a 1 or 2 second lag in audio feedback caused by server latency could literally cost them their life.
Your intuition is entirely validated by the research. In fact, the scientists who conducted the Prisma review identified high system latency as one of the most critical, unsolved, open problems in the entire field of assistive technology.
It is the melting point of the system's utility. The constraint just breaks the functionality.
Yes. Relying heavily on cloud-based APIs like Google Cloud Speech-to-Text or remote AWS image processing clusters introduces unacceptable risk. It requires constant high-speed, uninterrupted internet bandwidth.
Which you rarely have in a subway station.
Exactly. If the cellular connection drops, or if the phone's CPU overheats from processing the camera feed and throttles down, the interface catastrophically fails.
So what's the solution?
The research strongly dictates that for these natural user interfaces to be genuinely safe and reliable in critical environments, they must achieve a high degree of edge computing. The machine learning computation must happen locally, directly on the device's hardware, with near-zero latency, entirely independent of the cloud.
Which requires massive battery power and incredibly advanced mobile processors. This actually transitions us perfectly into our fourth and final section, implications.
It's all connected.
We have explored the atomic physics of the Jellium model, the theoretical debates of melting particles, the smart chemistry of hydrogels, and the digital frontiers of inclusive design. What does this all mean for society, the macroeconomy, and our daily lives? Let's begin by looking at energy, the environment, and economics.
The mastery of surface chemistry is not merely an academic pursuit. It is the absolute linchpin of the global green energy transition.
A perfect example of this is the development of proton exchange membrane fuel cells, or PEM fuel cells.
Yes, PEM fuel cells.
For those listening, PEM fuel cells are basically the holy grail of clean energy. They take hydrogen gas and oxygen gas, mix them across a membrane, and produce electricity, with the only exhaust byproduct being pure water. No carbon, no smog.
They are vital for the future of transportation and grid storage. However, the commercial viability of these fuel cells hinges on a very specific internal component called the bipolar plate.
What does the bipolar plate do?
These plates are responsible for conducting the generated electricity out of the cell, uniformly distributing the hydrogen and oxygen gases and flushing out the byproduct water. Traditionally, the industry manufactured these plates out of graphite.
Graphite.
Yes. Graphite works well chemically, but it is highly brittle, bulky, incredibly heavy, and very expensive to machine.
If you want to put a fuel cell in a consumer car, you need something thin, cheap, and strong, like stainless steel.
Precisely. The automotive and energy sectors desperately want to use metallic bipolar plates, specifically an alloy known as SS316L stainless steel. It is cheap, highly durable, and easily stamped into thin plates in mass manufacturing.
But there is a massive interfacial constraint. The internal environment of a working PEM fuel cell is incredibly hostile.
It is a fundamentally corrosive environment.
It is highly acidic, operating at high temperatures, with constant electrochemical reactions occurring.
Right. If you put bare SS316L stainless steel into a fuel cell, the highly acidic environment immediately attacks the surface atoms. The metal rapidly oxidizes and dissolves, releasing iron and chromium ions that permanently poison the delicate polymer membrane.
And that destroys the fuel cell.
In a matter of hours.
The macroscopic machine fails because the microscopic boundary is breached. So how do we fix the steel?
By engineering the surface at the atomic level. The research focuses on the impact of advanced surface pretreatments and thin film passivation coatings applied directly to the SS316L plates.
What do these coatings do?
By depositing a microscopic layer of conductive, highly corrosion-resistant material, such as titanium nitride or specialized carbon coatings, scientists completely alter the thermodynamics of the boundary.
They create a protective shield that conducts electricity but blocks the acid.
Yes, the success or failure of these atomic surface coatings is the singular defining factor in the long-term operational lifespan of the bipolar plates.
Wow.
Without mastering that specific interfacial chemistry, metallic fuel cells simply rot away, rendering hydrogen energy systems economically non-viable. The global transition to clean hydrogen power relies entirely on our ability to stabilize a boundary layer only a few nanometers thick.
The economics of a multi-billion-dollar green energy infrastructure scale entirely from the atomic surface. And speaking of energy implications, we also need to address the selective formation of metastable polymorphs.
This is a profound concept in solid-state chemistry. A polymorph refers to a material that can exist in multiple different crystalline structures while maintaining the exact same chemical composition.
Like diamond and graphite. Both are pure carbon, but they are radically different polymorphs.
Exactly.
And what does metastable mean in this specific context?
A metastable polymorph is a crystal structure that is caught in a local thermodynamic energy minimum. It is structurally stable for all practical everyday purposes, but it is not the absolute lowest, most relaxed energy state the material could theoretically achieve.
Right.
A diamond, for instance, is actually metastable at room temperature and pressure. Over millions of years, it technically wants to degrade into graphite.
So how does manipulating surfaces allow us to create new metastable materials?
By meticulously controlling the surface energies and manipulating the exact thermodynamic pathways during synthesis, often by growing the material on very specific lattice-matched substrates, scientists can essentially trap materials into forming these unique, highly energetic metastable structures.
Instead of their default bulk structures.
Yes, this allows us to force elements into unnatural, highly ordered geometries, opening up entirely unprecedented avenues for designing advanced, high-capacity energy storage materials and next-generation solid-state batteries that simply would not exist under normal equilibrium conditions.
Okay, so mastering the physical interface unlocks the future of green energy and battery tech. Let's shift our focus to the societal implications of the digital interface. Specifically, we need to talk about digital equity and inclusive design.
This is incredibly important.
I want to highlight a concept discussed in the accessibility literature known as the 85% problem.
The 85% problem is a stark framing of historical software development practices. For decades, the tech industry operated on the implicit assumption that it was sufficient to design digital interfaces that work seamlessly for roughly 85% of the general population.
And who is in that 85%?
This demographic represents the standard user, typically an able-bodied, neurotypical individual with unimpaired vision, hearing, and fine motor control.
And by optimizing exclusively for that 85%, the industry effectively abandoned the remaining 15% of humanity who live with some form of permanent disability, which, from a human-centered design perspective, is an abject ethical failure. Building a digital architecture that systematically excludes 15% of the population is deciding that those individuals do not get to participate in the modern digital economy, access online banking, or utilize essential civic services.
Fortunately, the structural landscape of the industry is finally shifting. And it is not merely driven by altruism or corporate goodwill, it is increasingly driven by strict legal mandates and international regulatory compliance.
Governments are recognizing that digital access is a fundamental civic right.
Yes, we are seeing the rigorous enforcement of standards like the ISO 9241210 framework for human-centered design. These international standards are forcing developers to adopt the paradigm of universal usability.
Which means?
The core tenet is that accessibility can no longer be treated as an afterthought, a patched-on feature implemented at the end of a software cycle. It must be woven into the fundamental DNA of the design from the very first wireframe. The interface must be universally accessible from inception.
And when you dig into the literature regarding how visually impaired users actually navigate these spaces, an incredibly important psychological concept consistently emerges: the internal locus of control.
In behavioral psychology, an internal locus of control is an individual's deep-seated belief that they possess autonomy, that their own actions, decisions, and commands directly influence and control the outcomes in their environment.
It is the feeling of being in the driver's seat.
Exactly.
For a sighted person, navigating a complex website is easy. You can visually scan the entire page in a fraction of a second, find the menu, and click where you want to go. You maintain a strong locus of control.
But for a visually impaired user navigating that exact same interface using a screen reader, the experience is strictly linear and temporal. The software reads out the code line by line.
If the interface is dense and poorly structured, the user gets lost in an endless maze of auditory gibberish.
And when that happens, the user's internal locus of control collapses. They experience severe cognitive anxiety, immense frustration, and ultimately task abandonment. They stop using the technology entirely because the interface has robbed them of their autonomy.
So how do software engineers code to protect and restore that psychological locus of control?
It often comes down to remarkably simple, yet religiously implemented interfacial features. For example, providing a globally accessible, universally responsive, easily locatable help button anchors the user.
Right.
They know that no matter how deep they get lost in the digital architecture, they have a reliable one-touch escape hatch back to a known state.
And from a raw coding perspective, it's about metadata.
Absolutely. The utilization of specific code features like the view.set content description attribute in Android application development is paramount.
How does that work?
If a developer builds a graphical button, say a magnifying glass icon for a search function, but fails to write a content description in the code, the visually impaired user's screen reader just hits the graphic and reads out raw, useless file names like button graphic 24px, or worse, it reads nothing at all.
Leaving the user completely blind to what the button actually does.
But by simply utilizing view.set content description to label the button as search database, the developer empowers the screen reader to translate the visual intent into meaningful audio.
It restores their autonomy.
Yes, setting clear, rigorous content descriptions allows the user to construct an accurate mental model of their environment.
But as the researchers point out, even if the software is architected with perfect universal usability and flawless code, we run headfirst into what the literature identifies as socio-technical barriers.
Yes, the software, no matter how elegant, does not exist in a vacuum. It is hopelessly bound to the physical hardware that runs it. And as we discussed, regarding the latency of natural user interfaces, running advanced, real-time spatial recognition algorithms requires immense computational power.
Which means the software has a strict, uncompromising hardware dependency. And let's be blunt about the economic reality here. High-end smartphones equipped with the multi-core processors, neural engines, and massive batteries required to run real-time AI computer vision without fatal latency are incredibly expensive.
Affordability is an interfacial boundary in and of itself. If a visually impaired user living on a fixed income cannot afford the flagship hardware required to run the accessibility software, then the perfectly coded universal design is functionally useless.
It's a massive barrier.
Furthermore, the physical durability and portability of the hardware are essential constraints. For a visually impaired individual, these devices are not just communication tools, they are their navigational eyes. If an assistive device is fragile and breaks easily, or if it is too heavy and ergonomically exhausting to carry throughout a 12-hour day, it fails at the fundamental interface of daily life. The industry must simultaneously overcome the software challenges of seamless API integration, the physical challenges of battery density, and the economic barriers of manufacturing rugged, highly affordable devices.
Which brings us to the ultimate synthesis of our entire exploration today, the merging of the worlds. You simply cannot separate the digital interface from the physical interface. They are entirely interdependent systems.
One cannot exist without the other.
Think about the massive stack of technology required to make something like the Guidecopter or the Transmigria app work. You cannot deploy an advanced, low-latency haptic feedback drone that safely guides a human being through a city without first mastering the chaotic atomic surface chemistry of the lithium-ion batteries that power its rotors. You need the highly stabilized, polymer-wrapped MZine heterostructures to manufacture the flexible conductive circuits inside the drone's sensory array. You need to meticulously shift the D-band center of transition metal catalysts to efficiently manufacture the carbon nanotubes that reinforce the drone's chassis.
And you absolutely need the atomic-level corrosion resistance of SS316L bipolar plates to keep the massive server farms running the Google Cloud APIs powered and cooled. The digital interface, with all of its sweeping software complexity, its human-centered design, and its algorithmic elegance, relies entirely At its foundation, on the thermodynamic stability of the physical interface at the nanoscale.
If the dangling bonds and electron oscillations at the atomic boundary fail, the hardware fails.
And if the hardware fails, the code fails.
As our understanding of these atomic surfaces deepens exponentially, and our digital interfaces become truly multisensory, predictive, and practically invisible, it raises a profound, almost philosophical question for the future.
It really does.
What happens when the boundary between our human biology and computational technology dissolves completely? If we can engineer smart, stimuli-responsive hydrogels that autonomously deploy targeted medicine in direct response to the pH fluctuations in our own bloodstream, and if we can deploy autonomous drones that guide us via intuitive, haptic, physical tension, will the interface of the future simply become an indistinguishable subconscious extension of our own biological senses? It is certainly something to mull over.
Absolutely.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
Yes, thank you.
And to our listeners, thank you for being part of this journey with us. We hope you enjoyed today's discussion. If you did, be sure to subscribe and support us in Patreon. And of course, you can write to us in comments if a specific topic needed to be covered, which help us all to grow. A small pause. Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.